Welcome to another HeatWise tutorial on psychrometrics. This is part 2. So this video will be going over psychrometric processes, so what heating and cooling and air mixing look like on a psychrometric chart moving from one point to another. So we'll do this by plotting some familiar points and seeing how what the lines look like in these processes when moving from one point to another. So we'll start with just a typical heating or cooling process, sensible only, so sensible heating or sensible cooling. Then we'll look at a more typical cooling process, which is both sensible and latent. Then we'll look at humidification, and then mixing of two air streams. So to start off, I've drawn a dot here at a very typical indoor air condition. So we've got 75 dry bulb at 50% humidity. So let's take a look at a heating process first. So in heating, this is a sensible only heating process. So heating, we're moving to the right on the dry bulb line. So if you recall from the last video, these numbers down here are the dry bulb values. So as you can see, they get higher as you move to the right on the axis. So adding heat to the air will obviously increase the temperature, and so you're moving in a rightward translation on this graph. So a very typical situation here would be taking room air on the return side of your air handling unit at around 75 degrees Fahrenheit and heating it to your supply air temperature. And the supply air temperature could be, let's say, around 95, maybe 90 to 95. So we'll call it 95 in this situation. And the important thing to note is that as you make this translation, it is perfectly horizontal because we're not changing the humidity in the air. As long as we're not adding humidification, and of course we're not dehumidifying the air, then you can expect a perfectly horizontal movement on this line. And our final point will be right about there. So you can see our humidity ratio stayed the same, which is about 0.0092. And of course our relative humidity has actually decreased. As our air got warmer, the air feels more dry. So you can see it's about 26 or 27% there. We're partway between the 20 and 30% humidity lines. So this would be a very typical and very simple heating process. We're just taking the air and we're heating it through our air handling unit and supplying it to the space. Now looking at just the reverse, a perfectly sensible cooling situation. It's of course just another horizontal movement on this chart in the opposite direction. So for example, if we did a perfectly sensible cooling to about the 60 degree Fahrenheit state, we would see our air land at about right there. So this is a perfectly leftward movement, and it lands us much closer to the saturation line. And you can now see why in a lot of cooling processes you actually see both sensible and latent cooling, because as you get closer and closer to that saturation line, you're going to have to start pulling moisture out of the air, because the coil temperature is likely going to be colder than whatever your leaving air temperature is, or it will have to be colder. So if your coil temperature is, let's say, 55 or 50 in this case, you would see some condensation on the coil, and we would therefore see latent cooling even before we hit the saturation curve. So while these perfectly sensible movements, right or left, are the simplest, they're often quite unrealistic, especially in the cooling situation. It's a pretty normal thing for heating. You just do perfectly sensible heating. As long as you're not adding moisture, then it will always be completely sensible. But in reality, our cooling processes are typically a combination of sensible and latent cooling. So I've plotted here a much more realistic supply air temperature. If you're running your return air at 75 Fahrenheit, 50% humidity through a cooling coil, you would see something more like this, where you're getting very close to the saturation curve, but you're just a little bit off of it because you'll never really be exactly on it. And this state here is at about 54 dry bulb and 53 wet bulb. So you can see it's more of a diagonal line that we've got here, and we're of course changing we're doing sensible cooling because we've decreased the temperature, but you can see there's also latent cooling involved as well. Our new humidity is approximately 0.0082, whereas our previous state was more around 0.0092. So about 0.001 pounds of moisture per pound of dry air have been removed from the Airstream in this kind of a cooling operation. And one of the most important reasons of why it's so necessary to have a proper understanding of the psychrometrics is, for example, if you wanted to achieve a particular state in cooling, let's say you had a very high latent load that you needed to condition, but you didn't want to overcool the space by supplying really, really cold air. That would be more of a dehumidification process. So let's say that you wanted to supply air at 55 dry bulb, but at about 50 wet bulb, so approximately right there. It's very difficult to actually just achieve that through the air handler through just the cooling coil alone. If your cooling coil is much colder, let's say it's got an entering water temperature around 45 or 40, you're likely going to be either cooling the air quite a bit below 55, or you're just never going to achieve that level of humidity without driving the air temperature much further down. So what you'd have to do in this kind of a situation is find the equivalent point closer to the saturation curve that you would need to achieve. So in this case, we could plot a point approximately right there at about the 48, 47 and a half, so 48 dry bulb, 47 and a half wet bulb point, and you can see that that is exactly at the same humidity ratio as our desired point. So this means that from our point 1, we would have to go to point 2 before getting to point 3. So we would dehumidify or cool from point 1 to point 2, sensible and latent cooling, and then we would reheat our air up to point 3. And as you can imagine, this can be a more energy intensive process because you're putting in energy to cool and then heat. And so there's a lot of, there are different strategies you can use in terms of conserving energy in such a situation, but the net result is that if you wanted to achieve this kind of latent cooling without going overkill with your sensible cooling, you would have to do some kind of a dehumidification and reheat type of situation. Now, something that's less commonly seen, but certainly not unheard of, is humidification. So humidification is common in places like hospitals where the humidity can't get too low for health reasons. So you would not normally have such a humid starting state, but let's say you were in a cold climate where you had lots and lots of fresh air, because it's a healthcare setting where you need lots of fresh air, and the fresh air outside is very dry. You might get a situation where your mixed air state is around 65 dry bulb and only about 20% humidity. And maybe you wanted to bring that up to a 75, 50 leaving air handling unit state. You would then have to, of course, both add sensible and latent heat to your Airstream. So you'd be adding humidity in this case. So it's the exact same process, just in complete reverse of the sensible and latent cooling process. You just need to make sure that you understand how much latent heat, and that therefore how much water is actually being provided to the air to create this new state. So we'll now go over one of the more complicated and also one of the more important psychrometric processes to study, and that would be the mixing of two air streams. So this is common when you're taking return air from your spaces and you are mixing it with outdoor air and then resupplying that, or conditioning the air first and then supplying it. So before you condition it, you need to know what is the inlet state on your cooling coil or your heating coil before it undergoes a psychrometric process. So let's take an example here where we have our typical room air at 75 degrees Fahrenheit, 50% humidity, and maybe the outdoor air is quite warm. It's on a design day at, let's say, 90 degrees Fahrenheit dry bulb and about 75 wet bulb. So way up there, very warm, humid air outside. So what we know is that the mixed air state is going to lie exactly on the line connecting these 2 points. So I've drawn a line in blue here showing the connection between these 2 points in a perfectly straight line. So when we mix these 2 air streams, we know that it will lie somewhere on this line. So that gives us a big helper in how we can narrow down where this mixed air state is going to actually exist on the psychrometric chart. The next question is how, where on this line does it actually lie? Does it lie closer to the warmer one or to the colder one? And of course the answer would be that it depends on the quantity of each airstream. So we can just take an example here. Let's say we have about 200 CFM of outdoor air and about 400 CFM of return air from the spaces. And the way to determine where exactly on the line that it lies is dependent on the ratio of these airflows. So you can see we have 400 and 200, and of course our total is going to be 600. That's just 200 plus 400. So the location of the point is going to be basically the ratio of, let's take our return air for example. So the ratio of our return air to our total air. So we just take 400 over 600, which is just 2/3. And that means that the point on our line is going to lie at the 2/3 point, but closer to the 400, because this is the heavier weighted airflow here. So because so I'll just write a 1 here and a 2 here. Our airflow 1 is twice as big. It means it's going to be twice as close, essentially. So we're going to have at approximately the 2/3 point, and what you'll notice is of the total length of this line, this length takes up 2/3, and this length takes up 1/3. So we literally just measure our line and then measure the points with a ruler to find our mixed air state based on the ratios of these airflows. So of course it could be done the other way. We could take the 200 and we would say 200 over our total of 600 is 1/3, and instead of measuring the 2/3, we would measure this 1/3 value from the opposite end. So this is an interesting way of determining where our mixed air state is. It's literally just using, drawing a straight line between the 2 points and using a ruler to determine where exactly it's going to lie on those on that line connecting the 2 points. So the last item I'll show you here for this video is actually the HeatWise Psychrometrics tool. So if we go into our browser here on HeatWise, so you can see I'm signed into my HeatWise account. I'm on the app here. Just simply go to Tools at the top and click Psychrometrics Calculator, and you will see a nice psychrometric chart, and we've got a point plotted on it. You can switch between imperial and metric units, and if you recall from video 1, I mentioned how the altitude can actually change the psychrometric chart. The one that we've been using is a sea level chart, which is fairly accurate for up to a couple thousand feet above sea level. But if you really wanted to get your results refined, you can actually enter the value from here. So let's say we were 1,000 feet above sea level. It will actually alter our psychrometric chart, and you can see that our altitude in the top corner here is 1,000 feet. And it changes the pressure, changes the look of the chart a little bit. And from this chart, we can enter our values. So we've got a 75 dry bulb temperature here, but maybe I will just change this to 84. And we can select what we want our secondary input to be. So right now it's at wet bulb temperature, but we can have whatever we want. Let's say 84 degrees with a relative humidity at, let's say, 65%. And you can see here it plots our point halfway between our 60 and 70% lines. That is our 80% or 84 degree Fahrenheit point at 65% humidity. And we can also add a point so that we can have multiple points plotted on our graph. So for our second point, maybe let's make this one a bit colder. Let's make it 55, and let's say our wet bulb temperature is about 53. So we're close to our dew point temperature, so this is more of a coming off the cooling coil, and you can see both of our points plotted there. So that is it for the HeatWise tutorial on psychrometrics part 2. In part 3 we will look at the actual math behind some of these psychrometric processes, so the math behind the cooling and determining enthalpy and so on. So we'll see you there.